Okay, recording started. Let's also bring in the telephone just to make sure.
Welcome to the CCC Confer Conference Center. For security verification, please enter your passcode followed by the pound or hash key. Please hold. Thank you. Your passcode is please wait. When you hear the tone, you will be the first person to join the meeting. The line will be silent until another person joins.
Okay, just in case anybody calls in, we have that covered. I'll start off by saying, does anyone have any questions on the Chapter 4 homework? Do you want to start there, or shall we just jump into Chapter 7? Okay, looks like we have a question on problem open traverses, okay? Aha, okay. I just looked up the question. Let's do this. Somewhere I should be able, there we go. New page. How do you find H? Okay. We have an open traverse that runs from A to H, and we're being given the deflection angles. So if the bearing of A to B is north 20 degrees, 40 minutes east, so let's see what that looks like. Okay, I apologize for my crooked lines. They're kind of hard to get perfectly straight here. So A to B, so if we have A here, we're going to be north to B, right? There's our north, 20 degrees, 40 minutes east. Everybody agrees with that so far? Okay. So it tells us that angle B is, or the deflection angle at B, I should say, is 6 degrees, 25 minutes to the right. Well, remember that a deflection angle, if you were setting up your instrument here at B, you would sight back to A, you would flip the barrel, right? So then you're extending this line here in a straight line. Oh, wow, straight line, there we kind of go. And then you're going to turn 6 degrees, 25 minutes to the right. So this is going to be exaggerated. But that would take us to point C, and that angle right there would be our 6 degrees, 25 minutes to the right. Okay? Then we'd be moving from C to D, and that is 3 degrees, 54 minutes right. So again, we'd be extending our line, and we'd be turning ever so slightly. There's D. To the right, there's our 3 degrees. At D, we're also turning to the right. Okay, to E, and there's the angle to the right. E is angle to the left, so we would extend E this way. We would turn 20 degrees to the left to get to F. Okay, and I've kind of run out of room to keep drawing, but you get the picture that this is kind of what it looks like. So how do we compute it? Well, A to B is north 20 degrees, 40 minutes east. That's here. Remember that our meridian north is the same at each station. So if this initial angle is 20 degrees and we went from that to here, then the azimuth of B to C would be A to B plus B, which would be 6 degrees 25 minutes. So that's going to give us B to C, which is, let's see, we've got 65 minutes, 26 degrees. We know we can't have more than 60 minutes, right? So what we actually have is that B to C is north 27 degrees 5 minutes east. Okay, so that's what the azimuth of B to C right here is. Now we know what B to C is. We're moving on to C to D. We're going to add the angle at C, 3 degrees, 54 minutes. Right? Does everybody visually see that? Does that make sense? Okay. All right, and it looks like, I got to double check here who's all with us, but it looks like Jonathan joined in. Okie dokie. Okay, so it looks like you guys have it, and that's what you do, and that's what it looks like. So what's going to happen when you get to here, when you're trying to calculate E to F? Exactly. I'm waiting for someone who's typing. Right. You guys are going to have to subtract it. So this is what you would do. Dot, dot, dot. Those aren't very good dots, are they? There we go. To get your azimuth of each segment all the way through. Okay? Are there any other questions from the Chapter 4 homework that you guys wanted to go over first? Or should we jump into Chapter 7 now? The Chapter 4 homework is due, I want to say this weekend for sure. I am looking it up. Hang on one second. Come on, Blackboard. Tomorrow. Yes, it is due tomorrow, Jonathan. It's due tomorrow evening by 11:59 p.m. But I wouldn't wait too long to get started on it. Again, I don't think it's terribly difficult, but it can be pretty time-consuming. And if you make a little error in there somewhere, the whole thing falls apart. So, and you end up having to start over. So I would recommend not waiting too long to get started on that homework if you haven't already. Okay. So I think we're all good. Yeah, I haven't assigned 7 yet. It will probably pop up yet today. It's the last big chapter that we're going to cover. We will still cover 5 and 6, but we will do that a few weeks from now. 5 and 6 are kind of like Chapter 1 in the book. They're very informational, but not computational. Chapter 7 is computational, and heavily so. So I wanted to make sure that you guys got a chance to kind of hear about it a little bit first, and then you'll have all this week to work the first homework on it, and then you'll have 2 more weeks after that to work on it as well, to work on some additional problems. So you'll have plenty of time to work through this. Now, Chapter 7 is also, as I said, it's computationally heavy, but it's also a little bit long. So there's no way we're going to get through all of these slides and all of these computations, but I want to get you guys started anyway. So here we go. Okay, so backing up. This chapter really focuses in on traverses. We've already been working with traverses in a very limited way. We measured angles and distances all the way around the Cowsley building, and you guys calculated the misclosure error of your angles. That's just the start of what you need to do to balance that traverse. So there are open traverses and closed traverses. Open traverses, you need to use deflection angles. Closed traverses, you use interior angles. If you have to go out and create your own traverse from scratch, in other words, the ones I've been giving you, I've set the points, I've told you where the points are, and you're measuring those points. But if you had to go out and say, measure someone's property, you would have to set those individual points around that property. So where would you put the markers? Well, you want clear lines of sight. The longer the better, and the fewer setups the better. So you would have to evaluate the lot or the lots and determine where you think it would be best to put locations. Okay, here's an example of an open traverse. We are going to be calculating deflection angles in a lab when we meet this coming Friday. So you'll see what this is like in person. Here's a sample of some field notes for an open traverse, where you'll notice, let's see if I can get this to work. Yay. You'll notice here, this column, left, right, and these indications here. This is really critical. Deflection angles are only of value if they have a left or right designation, so it's extremely important that you record those in the field book. Okay. Sample of a closed traverse. Again, that should hopefully look pretty familiar by now. Okay, so here's what we're going to do in terms of our traverse computations. The first thing you need to do is balance all your field angles. What does that mean? It means that when you measure all of those interior angles, you need to determine how close they are or how far off they are from the geometrically determined sum of those interior angles. Whatever the error is, if the error is too large, you need to go out and remeasure again. If the error is within tolerance, then you can go ahead and make your actual corrections and balance those field angles so that they sum up to what they're supposed to sum up to. You may actually have to adjust some of the field distances once you balance those angles. Then you're going to need to compute the bearings or azimuths of each segment of your traverse. I recommend working in azimuths. It's just easier to do the calculations. Then you're going to compute your linear error of closure and the precision ratio of the traverse. We will see how to do that in just a minute. We're then going to compute our balanced departures and latitudes. I'll show you what those are. And then you're going to compute, let me move this. All right, come on. There it goes. There we go. Then you're going to compute the rectangular coordinates and ultimately the area of that traverse. Okay, so here's an example. We'll slowly work through the example. So we have one, let me put my pen back on so we can, come on. Okay, so we have a traverse that has 1, 2, 3, 4, 5 sides, 5 angles as given. The first thing we need to do is balance those interior angles by determining our angle misclosure. This should be familiar. You've already done this at least a couple of times. So the difference between the sum of your actually measured angles and the geometrically correct total for the polygon is what we're looking for. We know that n minus 2 times 180 will give us what we're looking for. So then we're going to apply an average correction to each angle. You can also apply larger corrections to angles where poor conditions were present, but for our purposes, we're going to stick with an average correction to each angle. So let's take a look at what this looks like. These are the same stations and angles we were just looking at from the previous slide. Here's the angles. There we go. Here are the angles here that were measured in the field here. They sum to 539 degrees, 59 minutes. We know that they're supposed to sum to 540. So the difference between 540 and 539.59 is 1 minute. So we know that our error or our misclosure is 1 minute. And we're going to go ahead and correct for that. There's 2 ways to do that. The first way that we're going to use for the most part in this course is this here, equally balanced. So we're taking an average correction. So 1 minute is equal to 60 seconds. We have 1, 2, 3, 4, 5 angles. So we divide 60 by 5. It gives us a correction of 12 seconds per angle. Do we add the correction or subtract the correction? Right, we add it because we're low, right? Here, we're a minute under, so we need to add that minute back in. So we're going to add 12 seconds to each measurement, which is you can see what they did here. And now we total again, and we equal our 540, which means that we're balanced. Okay? The other method that is an option for surveyors, but not what we're going to do, is arbitrarily balancing the angles. And you can see here that 80 degrees, 58 minutes, 30 seconds became 80 degrees, 59 minutes. So they took half the error and tossed it here. And then they took the other half of the error and tossed it here. It is arbitrary. It is based on the surveyor's judgment. It could have been that these 2 were relatively poor shots. Hard to say. But for our purposes, we will go ahead and use equally balanced. Okay. So now what we need to figure out, if we look back at our list, let's see. There we go. So we did this. We can check our little box here. We balanced our field angles. We're not going to worry about this for the moment. So the next thing we're going to need to do is compute our bearings and azimuths. But unfortunately, the order of my slides has us calculating departures and latitudes. Whoops, I went too far. There we go. Okay, so let's define our departures and latitudes. Simply, put my regular pen back on. Here's A. Here is B. That's supposed to be a straight line. There are multiple ways of getting from A to B, right? You can walk along this line right here, this very crooked line I drew that's supposed to be straight. Or couldn't you walk over here, turn 90 degrees, and then walk this way up to B? Or you could head this way from A, turn 90 degrees, and get to B that way. So basically, these components of our line are our latitude and departure. By definition, the latitude is your change in the y direction, which is the same whether you walk it first or second. And departure is our change in the x direction. We know that these are right triangles. So again, by definition, the distance times the cosine of the angle will give us the latitude, and the distance times the sine of the angle will give us the departure. So ultimately what we have are the north-south rectangular component of the line, and then the east-west rectangular component of the line. So here's another example. This is different ways for us to locate a point. So we're going to go from point D to point A. We're traveling a distance of 63.642 feet. I don't know, maybe it's meters. I don't have any units here. And where are we walking? Well, we're walking north 29 degrees 53 minutes east. So that this information here specifically identifies this line from D to A. Tells us how far to go and in what direction. We can calculate our departure, which is here. Let me put my little highlighter back on. Here we go. Here's the calculated departure, and here is the calculated latitude. And how they were calculated, I'll grab my calculator here, is, looking back at our previous slide, the latitude is equal to the distance times the cosine of the angle. So the latitude is equal to the distance, 63.642, times the cosine of our angle, times the cosine. What is our angle? 29 degrees, 53 minutes. Degrees, 53 minutes. And if you punch that in your calculator correctly, even though I know it's difficult to read my lovely writing there, let's multiply this out. Check it out on your own calculators. Make sure that it works so you can prove to yourself that it does. Did someone just join us on the telephone? So it gives us 55.180. 55.180. And as I said, that's our latitude. And there it is right here. Okay? Oh, Jonathan's raising his hand. Yes, Jonathan. Not in this instance, no. The longitude and latitude are coordinate values, and these are just components of the line. So these are not the same latitude. Okay, and then we would calculate our departure here in the same way that we calculated the latitude. So it would be 63.642. Let me see if I can get this written in here. The departure would be equal to 63.642 times the sine of 29 degrees 53 minutes. And if you punch that into your calculator, that should give you 31.709. Okay? Latitudes and departures. Here's the cool part about the latitudes and departures and why they're important. Okay, we are looking at a four-sided figure, A, B, C, D. Come on, there it goes. Okay, we are looking at it in a counterclockwise direction, counterclockwise. So we're going from A to B, B to C, C to D, and D to A. Notice that each one of these can be broken down into your latitude and departure. So the distance from here to here is the latitude of AB. The distance from here to there is the departure of AB. Then when we move from B to C, we have the departure of B to C, then the latitude of B to C, the departure of C to D, the latitude of C to D, departure of D to A, the latitude of D to A. Notice that there are signs associated with all of these, and that's extremely important. When you are heading north or east, that's considered positive. When you are heading south or west, oh goodness, having a hard time, there we go, that's considered negative. So the direction that you're traveling, counterclockwise in this case, is important to know because you have to remain consistent all the way around your figure. So the reason that your latitude of A to B is positive is because you're heading north. The departure of A to B and the departure of B to C are both negative because you're heading west, and so forth around the figure. Well, if this figure is perfect, wouldn't it make sense to say that the sum of the departure of AB plus the sum of the departure AB and BC should equal the sum of the departure of CD and DA, right? Because the distance from here to here should be the same as the distance from here to here. And the same would apply to the latitude. So the distance from here to here should be equal to the distance from here to here if this is a completely balanced figure. So when we compute our departures and latitudes, we started out by balancing the angles. We then compute the azimuths of each segment around the traverse, and then we compute our latitudes and departures. Even though we perhaps balanced all of these interior angles so that they equal 360 degrees, oh no, what's happening? Oh, there it goes. You may also find that even when you do that, the sum of the departures and the sum of the latitudes do not equal to 0. So computation of our departures and latitudes, balancing our interior angles. So we're back to that original figure that we started with, the five-sided figure. And here are all of our angles here. There's our angles and all of our distances around the figure. Here, 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 and here. Okay, now, isn't that what you measured in the field? The last time we had lab, you measured angles and distances. So we're going to take those and balance our interior angles, which is what's been done here. Then we're going to take the next step, which is what you did in Chapter 4, and you're going to calculate the azimuth of each segment of your traverse notice that it was done in a counterclockwise direction. Come on, pen. There it goes. Counterclockwise direction using azimuths because that's the easiest, right? You just add that interior angle to the back azimuth of the previous course. Much faster, much easier way to do the calculations. I'm trying to get my pen back. It's not cooperating. There we go. Okay. So that's what's shown here. And now, here's all the actual computations. Here it is in tabular format. So here's the distance of each of the segments that was measured in the field. Here's the calculated azimuth, also translated into a bearing. You don't need to do that. And here are the calculated latitudes and departures for each one of these segments. Does everybody understand where these numbers came from, or do you need me to go through one or two of the calculations? Okay. Alrighty then. Okay, so remember we said that the sum of our latitudes and the sum of our departures should be equal to 0, right? So if we go back to our figure here, it'll be a little bit easier to see, right? And we have latitudes and departures, poorly drawn, but latitudes and departures nonetheless. Like, here we go. There we go. There it goes. So remember that all of the latitudes here should equal all the latitudes here, and that all of the departures here should equal all the departures here. But if you look at it on the chart, on the table, here we go. Funny. Our latitudes are just a tiny bit off, and our departures are just a tiny bit off. So we're going to go ahead and calculate that error. What does this error visually look like? What that error means is that if you started here at A, and you went to B, and you went to C, and you went to D, and I'm not drawing this exactly right, and you went to B, E, there we go. When you came back to A, it means you actually came back somewhere else. This is greatly exaggerated, by the way. But it means that right here, you're off somewhere. So, making this here and making it a whole lot bigger, what we need to know is this right here. This is E, visually. Not E here, point E, but E, the calculation E. And what we need to know is this. Or what we know, I should say, not need to know. But this latitude of plus 0.06 implies that your 0.06 here off, oops, I went the wrong way, and this 0.49, it's actually negative, so I drew this the wrong direction, because remember, you have to travel in one direction, whether it be clockwise or counterclockwise. But this distance would be 0.49. It would just have been in this direction. So here's the 0.49, and there's our A to A here. So what we're trying to figure out is how far off are we between where we started and where we ended up. And this error in our latitude and departure tells us exactly how far off we are. So this calculation is simply the Pythagorean theorem using the latitude and departure to determine the length of the line between where we started and where we actually finished. Our precision ratio tells us how good our traverse is. You take your error and divide it by your perimeter. There's the perimeter, the sum of all of the distances. Remember that you always want a 1 on top, and you'll round up to the hundreds on the bottom. So how did we get from 0.49 divided by 2081 to 1 over 4247? Any guesses? How do you get from here to here? Okay, Kathy, if you were actually to divide this, you would have a decimal here. Sandy is right. You divide the top and the bottom by 0.49. Any number divided by itself is 1. What you do to the top of the equation, you need to do to the bottom in order to keep it in balance. So 0.49 divided by 0.49 is 1. That's where this 1 up here comes from. And then 2081.19 divided by 0.49 gives you 4,247. And then we simply round to the 4,200. So this particular traverse is good in 1 to 42,000. The precision of this traverse is 1 foot in every 4,200 feet. Okay, this is the book's drawing of what I was just telling you about. So it was telling you that basically, even though you're starting and ending at A, you're a little off. How far off are you? This right here is the blow up of this part. So you're off by this much in latitude and this much in departure, calculating out your error here. You can also calculate out the bearing or azimuth of this line so that you know exactly where it is, which they are showing here. But this is our linear error of closure, which is that E calculation we were just looking at. Okay. If you have an unsatisfactory precision ratio, so you went through this whole process and you were told initially that your traverse needs to be good within 1 in 5,000 feet, and you calculated it out, and oh no, it's 1 in 4,200 feet, then you can start out, oops, too many slides. You can start out by first double checking all your computations. Before you run back out into the field and spend time in the field, double check that all the math you've done and all the measurements and everything is written in the book correctly and that you don't have any actual errors there. So double check all your field book entries and double check your math. Then you want to go ahead and compute the bearing of the linear error of closure and check to see if it's similar to a coarse bearing. If it is similar, very often that's the line or segment that you made an error on. And if you are going to go back out and remeasure, that's where you would start. If you still can't find the error, you're going to have to remeasure the sides of the traverse. And when a correction is found for a measured side, recheck your computations to see if you meet the required precision level. So in other words, you don't have to do the entire thing all over again. Just see if you can track down the side that seems to be causing the biggest problem, fix it, and see if you're now within tolerance. Okay. You're going to need to make additional corrections or adjustments when your latitudes and departures are off, as they often will be. You need to correct for that because you're going to use these values to compute the coordinates of each station, and you need those coordinates to compute the area. So your algebraic sum for your departure and latitude must be 0. How do we do that? How do we make that correction? We use what's called the compass rule adjustment. And I know this looks very complicated, but it really isn't. The compass rule adjustment basically makes a correction based on a ratio of the error to the distance between the points. So here's a sample of those calculations. So the actual formula for this is the correction of the latitude for the segment A to B. You take the sum of the latitudes, you multiply it by A to B, the distance A to B, over the perimeter of the entire traverse, and that will give you the correction value. So what you find here, though, if you rearrange these terms, is that you're taking the distance of the segments and you're multiplying it by the sum of the latitude divided by the perimeter. These two values never change, right? The sum of the latitude is what it is, and the perimeter for that particular traverse is what it is. So you can calculate this and then multiply it times the distance of each segment to calculate that correction. So here's the samples. So correction of the latitude for A to E, 0.06 was our latitude misclosure. 2081.19 is our perimeter. And we're going to multiply that by 350.10, which is the distance of A to E, etc., 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 for all of our latitudes. Now you can do a check, right? Again, we're correcting for error. What is our latitude error? 0.06. So how much correction should we be making? 0.06. So we're distributing 1 there, 2 there, 1 here, and 1 here. 2, 3, 4, 5, 6. Our corrections equal. What do they need to equal? How did we distribute it? It's distributed based on a ratio of the distance of the segment to the total distance. So the longer the segment, the higher the correction. The departure works in exactly the same way. The correction for the departure of a segment is equal to the sum of the departures times the segments divided by the perimeter of the traverse. Again, these two values here are constant for each traverse. Sum of your departure, perimeter, multiply that times your segment distance. In this case, we're correcting for 0.49. So you can see again, it's proportional to the distance of the segment. And if you were to add these up here, they would equal the 0.49 correction. Everybody still with me? So far, so good? Yes, it's a lot of information. This is a lot of information. And as I said, I know you haven't read any of the material, so it's hard to follow. But I'm hoping that when you start reading it now and then start practicing some of the problems, it'll start clicking into place. And I'm in my office all week, so by all means, please ask questions. Okay, so we're using our compass rule in order to calculate the correction that we need to apply to each latitude and departure to bring the sum to 0. So the table's getting bigger, which is why the print's getting smaller. This is the same initial table that we started with that had the individual segments, the distance of each segment. They're using the bearing. I would continue to use the azimuth. We know how to convert back and forth between them. Here are your initial calculated latitudes and departures, and you can see here, here's those errors. Here in these two columns, and I do recommend, by the way, that you put these into a tabular format. It does make it much easier to follow and to check. Here are all of the individual corrections that we just calculated. Right here on this particular slide, we just took all of these values and transferred them into the table. And now we're going to apply across. So, if I can get my other pen back. Come on, pen. Come on. No. There we go. So, to correct the latitude of A to E, and you really need to pay attention to your signs here, we have negative 311.30 minus 0.01, and that is going to be equal to negative 311.31, which is right here in our table. Okay? Then you would take positive 246.10, and you're going to subtract 0.02. That gives you the plus 246.08. And so on and so forth through the table. You just have to be careful that you're actually matching the latitude with the latitude corrections and the departures with the departure corrections and getting them in the right place. Here's how we know that we've done it correctly. Ta-da! Ta-da! The sums of our departures and the sums of our latitudes are now equal to 0, where they were not before. So we've taken the corrections, we've applied them correctly based on the compass rule, and we now have 0 and 0 for our balanced latitudes and departures. Yay! What this slide is telling you is that all of your trigonometric relationships apply between any 2 points of your traverse. So if you know the latitude and departure of a segment, you can calculate the distance of that segment. If you know the latitude and departure of a segment, you can also calculate the bearing or azimuth of that segment. Okay, so let's take a look here. This is just a continuation of the same table. Here are our balanced latitudes and departures. Now that we have the balanced latitudes and departures, we can actually recalculate the distance between A and E, E and D, D and C, based on these corrected latitudes and departures. So what it's showing you is that the distance between A and E is equal to the adjusted latitude squared plus the adjusted departure squared, which is equal to 350.14 feet. If you remember from our previous table, the distance that we were using for A and E was 350.10. So once we've made that correction, we can adjust the actual distance of each of our segments. We can then also adjust our bearings or azimuth. And here's the comparison between the original and the adjusted. Okay, the other thing you can do is if you do have a traverse, A, B, C, D, but perhaps you can't see between D and A, or you weren't able to measure it, you can actually close this traverse using your departures and latitudes. What you need to know and be careful of is that if there is any error in this traverse, you're throwing all that error into this final computation, because you have no other way to balance everything other than make this fit and force this to fit on this last segment. So what do we know? We know the departure and latitude of 3 of the 4 segments, which is what you're seeing here and here. And we know that these have to be equal to 0 in order for this to close. So the sum of your latitudes is equal to negative 202.82, and the sum of your departures is 276.13. That becomes this departure and latitude here, which allows us to then calculate the distance and the bearing of the line here between D and A. Okay, getting on to the last piece. Yay, which is good because we're running out of time. Rectangular coordinates. Rectangular coordinates are simply, these should again hopefully be familiar. Again, I apologize for the crooked lines. I'm doing the best I can. Remember way back in math class, you had your y-axis and your x-axis, and if you had a point here, and you had a grid, right, that kind of went like, let's say like this. Okay, so if this was 1, 2, 3, 4, 1, 2, you would say that the coordinates of this point here were 2, 4. Right? That should hopefully be familiar. We're essentially doing the same thing with just a teeny beeny weeny little twist. Okay, in surveying, we don't use y and x. We use north, south, east, and west. So this becomes north, this becomes south, this becomes east, this becomes west. And then to confuse you just a little bit more, what we actually use is only one quadrant, which is northeast. So you'll find that everything will be given in terms of coordinate points as a northeast coordinate. One other thing to pay close attention to is that the northern coordinate is always listed first. So even though here we're more likely to see this as 4, 2 because we would always see it as x then y, in surveying you're going to see it as y then x, okay? Meaning north then east. So let's take a look at this original traverse, right, that we were looking at earlier, A, B, C, D, E. We've balanced the departures and latitudes, which you can see here for each segment, right? They're all listed here. And what we've done is we always want this to be in the northeast quadrant. So we've made an assumed value of our initial coordinate. We want to make it such that we never cross south of our east-west line and that we never cross west of our north-south line. So we're going to assume that station A is 1,000 north, 1,000 east. If I am located here at 1,000, 1,000, and I travel, let's go counterclockwise. If I travel 311.31 feet south, then what's my northern coordinate of E? 1,000 minus 311.31 gives me the 688.69, the northern coordinate of E. If I start here at 1,000 and I travel 160.27 feet east, then my eastern coordinate is 1,000 plus 160.27, giving me the 160.27, the 1160.27. If I'm now moving from my eastern coordinate, northeast here, and I'm traveling another 524.27 feet east, I take this coordinate and add my departure. That gives me the eastern coordinate of my next point D. Okay? So you can see how you calculate your coordinates all the way around your traverse. Again, we're going in a counterclockwise direction. Everybody with me? Okay. This is the same thing in a tabular form. So here are all of those balanced departures and latitudes for each of our segments. notice the way this is written, right? Because the coordinates are at an individual station. So station A is at 1,000, 1,000, but the departures and latitudes are tied to the actual line segment, not to the station. So you can see that there's gaps here, but they make sense. So we're going from A to E. The balanced latitude, the balanced departure, we add them and that gives the 688 and the 1160. E to D, etc., all the way through. How do we know we did it right? Well, when we get back to A, you should be back to the coordinates you started with. Okay? So this is the same thing we just talked about on this diagram visually in a tabular format so that you can see all the calculations. We're going to skip this for now. Skip. Skip. Okay. So going back to that slide from the beginning, we balance the field angles. If necessary, you correct the field difference, the distances. Then you compute the bearing or azimuth. Stick with your azimuth. It's much, much easier for each line segment. Then you need to compute the linear error of closure. Remember, that's our E value, basically using our Pythagorean theorem, and our precision ratio. We then compute the balanced latitudes and balanced departures. That's using the compass rule. We then use that to compute all of our coordinates. That's how far we've gotten. You then take those coordinates and you calculate the area. So we're skipping a bunch of stuff here. Area by coordinates. Okay, this is the formula you're going to use to calculate the area by coordinates. It looks very complicated. I'm going to show you an easier way to do this. Basically, what this says is that 2 times the area is equal to x sub A times y sub B. Okay, remember that our x coordinate is actually our easting and that our y coordinate is our northing. So the easting coordinate for point A times the northing coordinate for point B. That's what this represents. Plus x sub B, y sub C, which is the easting coordinate for B times the northing coordinate for C, etc., through the whole thing. This is being applied to a 4-sided figure because you have A, B, C, D. You need to make sure that however many sides you have, you put in that many terms. Oops, I didn't do it. Okay, I thought I had another slide here. So what you're actually going to do is put your, we are so out of time. You're basically going to be cross-multiplying. So if you list all your eastings, you have to make sure that you go back to where you started. Come on, move out of my way. There we go. So if you list all of your terms all the way down for both, then you multiply from here to here, here to here, here to here, here to here, okay? But what you have to make sure is that you include this A again, or whatever the station is that you started with, you have to end with. And you would take those, sum them up, and that'll give you a single value. Those are your plus values. Those are your A to B, right? A to B, B to C, C to D. Then you go this way, and you multiply in this direction, all the way down, okay? You add those up, and those are your minus components here. So you're going to have a value. You take the difference between these two values, divide it by 2, and that gives you the area. Now remember that in most instances, all of these values are feet. So when you calculate this area, this is actually going to be feet squared, and you'll need to convert it to acres. Okay? I know that's very quick. We can go over that again later. We can talk about it at lab probably this coming Friday, but we've hit our hour mark, and I just wanted to make sure that you guys kind of got a quick overview, and this is a really quick overview. Are there any questions on this at this point? Guys, please, please. Okay. Okay. Well, spend some time, read the chapter. I will get the assignment posted probably yet today. You'll have till next Sunday to complete the Chapter 7 homework. Like I said, I'll try to answer some questions for you on Friday at the lab. I think we'll have enough time to do that. And you will actually be doing this with your own data in the lab on Friday. So one of the labs will be a deflection angle lab. And I'm trying to think, I haven't decided yet if we'll do that one first or second. And the other lab that you're going to do will be a traverse lab. It will not be the Towsley traverse. We'll have a new traverse for you. You're going to go out in the field. You're going to measure all the angles and distances. You're going to come back into the classroom and calc all of this out so that you can tell me the area of the traverse that you measured in the field. Okay? So it's a really good idea for you to look at this before next Friday, because this is what you're going to be doing in lab on Friday. The homework still won't be due till Sunday, but you might want to make sure you spend some time on this before Friday. And I will send out an email or an announcement that says the same for those of you who, or for the students who didn't join the session today. Okay? I don't want to keep everyone too long, so awesome. Kathy, if you have questions tomorrow or during the week, please, please, please call me, send me an email, and I will walk you through all the various steps. Hector, the same for you. Anybody, I mean, that's the same for anybody, but I know that Kathy had said she was a little bit confused, so let me know. Have a terrific weekend, and I will see you guys all on Friday. Thanks. See you later. Oh, stop my recording.